All right, now that you've learned how to analyze categorical to numeric relationships, let's learn how to visualize them. So I'm going to start out by using this bike buyers data, which is where I got that education and income data from before that, because it'll give me a chance to do a little bit of data cleaning that could be useful and interesting or helpful to you. So I'm just going to copy and paste straight out of that chapter, 18.1, or it could be a different number in your book. This is the bivariate cat-num viz chapter. And we're going to start by simply pulling in a few packages we're going to use and the data and taking a quick look at it here. I'm going to close these out. All right, so next thing we want to do, we want to clean the data to a certain degree to make this analysis a bit easier. Now, before posting this data set, I went ahead and converted some of these categorical features to numeric features. So marital status is married and single are the only two statuses in here, and I converted that to a dummy code, 0, 1. Same thing with gender, and even education, where education has those 5 levels we learned in the last chapter: partial high school, partial college, bachelor's, and graduate. And I converted that into a number. And there's a reason for that. It's going to help make my bar chart. I can order it by the implicit level of education. Even though education's a category, there's an order to it. And so I want to show you how I came up with these columns right here. First of all, let's find each of the unique values of education. df.education.unique. That gives us our nice array here so we can see those 5 values. Let's make a new feature now called df education rank, since I already have one called education numeric. I'm going to set this equal to df education. Now, I don't want to overwrite education because as you'll learn later in the book, we sometimes like to treat these ordinal features as categories and sometimes as a rank ordered number. There's advantages and disadvantages to both. If we treat it as categories, well, let me go back to the other one. If we treat it as a number, like we're about to do right now, then that captures the fact that one level of education is higher than another. But it assumes that the difference between each level of education is the same. For example, that the difference between partial high school and high school is the same as the difference between high school and partial college, which may and likely often is not true. So we make 2 versions, a numeric version and a categorical version, and later on we're going to try out both versions to see which one is a better indicator of our label when all the other variables are included. But for now, let's just learn how to create this numeric version. It's pretty straightforward and easy. I'm going to, now that I've got this new feature, I'm simply going to say df.education._rank, and I'm going to use the replace function. And there's a few different ways we can use this. The first way I'm going to use it is by putting in a list, but you know what, I don't want to take the time to type it all out, so if you're one of my students in this class, just go to the book to 18.1 and let's copy this list right here so we don't have to type that in. If you're watching this on YouTube, sorry, you can just copy this by hand and pause the video if you need to. Whoops, try it one more time. There we go. So I put in one list of the values that I want changed, and then my next list of the values to change it to. All right. Finally, make sure to set in place equals to true because, as you might remember, it does this on a copy of the data frame, and we want it to be done on the original. So let's just take a look and make sure that works the way we're expecting it to. Okay, beautiful. 4's for bachelor's, 1's for partial high school. That looks good. Last thing you need to do is notice right here, dtype int64. Now, it's because I previously did this in memory. Yours might say dtype object right here. And so if it does, then that means you're going to want to change your data type. It means because it started off as, right here, it started off as a string or as an object. Once we replace the values, it didn't automatically change these to numbers. So if it doesn't, you may need to come in here and use as type and change that to int64. There we go. So if yours gives you any trouble, if you have any errors, often it's because you didn't spell one of these right and so it didn't find it and it left in one of those values. And so the replace didn't work. Like when I first did this, I just typed in graduate and then I didn't notice because there weren't any graduates in this list right here. All the words graduate were still in there. All the words graduate degree were still in there and I didn't know how to change them, so that's usually what goes wrong there. Let's go ahead and do the same thing with commute distance numeric, or commute distance. And I'm simply going to copy this right here. And we're going to call it commute rank. Oh, whoops, I clicked on the wrong, I'm way off here. One sec. Here we go. All right. Now, here's what I've done differently with commute rank. Education, like I said, it's ordered, but the difference between each level can be different. Commute distance, we have the same issue. This is text, so it's an object. However, there is a literal distance that we know between each one of these levels. So rather than replace it with 1, 2, 3, 4, 5, I've decided to replace it with the lower bound of each one of these ranges. So I can at least capture that distance between each one of these things. Here, I just want to show you another way to use as type. If I don't specify the series first, I can input a dictionary and specify a column name and a data type there, and I can add as many of those as I want with commas and keep doing a key value pair. Anyway, let's go ahead and run that one too. As type doesn't need to be done in place. It happens in place. That's a rare exception. Lastly, what else do I want to do? Purchase bike, we need a numeric version of that, but I already have one in there called purchase bike numeric. So one thing that I'll show you is in the book, once you go through and create all these cleaning steps for a particular data set, it's nice to turn it into a function like I've done here. I've just made this clean bike buyers, which means import the data. Let's make each of these numeric versions. We're gonna, looks like for whatever reason, I decided to convert purchase bike in place here. I go through, use all these replace features, cast things back the way they should be, and then return the data frame. So that means what I can do now, I'm gonna save that in memory, and I'm just gonna say df equals clean bike buyers. And so I don't have to go back and run each one of these things one at a time. In fact, I'm going to go through and delete and simplify. And you know what? I'm even going to drop this one right there. And I'll bring these down. All right, we got everything we need here. Let's go ahead and work on a bar plot. We're not going to use Matplotlib much anymore. I'm going to skip right to the Seaborn versions, which often look a bit better and are a little bit easier to use since they're meant to work on top of Matplotlib. Anyway, we've imported Seaborn above here, so let's go ahead and create an snes.barplot. For barplot, we're going to pass in, let me show you something. Let me do it the wrong way first. Well, technically it's not wrong, you'll see what I mean in 1 second here. We're going to pass in the x and then the y. All right, run that. That's the bare minimum that you need. Let's get rid of a few of these things up here. First of all, we don't need this object description here. Semicolon, whoops, not that. A semicolon or a plot.show will get rid of that, but we still have this future warning here. It says, pass the following variables as keyword arguments. For the latest version, the only valid positional argument will be data, meaning positional argument is an argument that you put in a certain position in the list of parameters. And when it's in a certain position, then Seaborn knows what that parameter is intended to be. But they're shifting, only the data df can go right here. And now they want us to use either this, x equals education, and y equals purchase bike. That'll, oh, what did I miss here? Y equals, did I spell that wrong? Nope. Oh, right here. we have to say, if we do it that way, we have to say data equals df. So that's one way. Or we could simply say, as long as we use x equals and y equals, we can go back to df education like that, and y equals df purchase bike like that. That'll also work. Either one's fine. All right, so we've got our first bar plot. But as you can see, we have a small problem. We have, first of all, the ordering of the bars are alphabetical instead of greatest to least. And then also we've got some crossover. So let's fix this issue here first. To do that, I'm going to start by showing you one way, which would be to simply adjust the figure size. And so since we've imported matplotlib as PLT, we'll still use that plot object often in Seaborn to make customizations like this one. So when I say we're not going to use matplotlib, I just mean we're not going to use it for the actual viz. We'll modify it though using the plot object. So plot.figure, one parameter is fig size equals, and then we put in here width comma height. So let's just expand this a little bit to like 10 comma 5 so you can see what that'll do. There we go, pushes it across. Now they're not overlapping. Well, maybe you don't want them to be that wide. Can you just rotate them a bit? Yep, exactly, that's the next step. So to rotate them, we're going to use, we're going to have to first set it equal to a viz object like this, viz equals, now I'll grab, my sns.barplot. And then we're going to use that viz object to then set xtick labels. There we go. And then we're going to, first of all, set the labels. We have to put the values back in again, bachelors through through all of them. So to do that, we can just get the tick labels that it currently has. So viz.get xtick labels. There we go. And that's a method. And then we'll pass in the rotation we want. Let's do it about 25 degrees. That ought to do it. There we go. Oh, well, so we don't get this to show up, let's not forget to add that. Or again, remember, we can always do down here plot.show. That should take care of all that too. Okay, that's looking pretty good. Let's now learn some other features here. So, oh, you know what? I forgot. We're going to reorder this. So let's do that next. I'm going to keep these. And I don't like the extra line of code. I prefer this semicolon method right here. But one other thing I want to do is add a new parameter here to our barplot object called order. So I'm going to put this down to the next line. It starts to get pretty long, this list. And I don't want to have to retype everything in, so I'm going to grab the proper order from right here. There we go. So yeah, this list is in order from least education to most. I'm going to copy that in right here for order. Run that one. All right, here we go. Partial high school to graduate degree. And as we can see, as people get more education, they seem to purchase bikes less, probably because they're buying cars with their income and don't need them, but there's a slight uptick on graduate degree. Maybe it's because they're poor again, going back to school. So let's do something else. Let's first of all, now that we have that, what are these tick marks you've been seeing here? We haven't really talked about that yet. Well, by default, those tick marks represent an estimator of the amount of error in each one of these, or the variance in each one of these different groups, the variance in purchase bike in each one of these groups. Well, we can adjust that and make this bar represent anything we want. So for example, I'm going to come up here, and because we're using this technique where we use named parameters, we can put the parameters in any order we want. I'm just going to fill in this space right here with one called estimator. We're going to set this equal to, how about the median value instead of, oh, maybe I should put in a comma. And besides that, I'm going to need to pull in median. Have I pulled in NumPy yet? I think we did. Yeah, right there. So now that I have NumPy, we're just going to set this to np.median. All right, so what the crap happened here? The bars, So I should have specified before, the estimator is what this bar represents right here, not this little tick mark. The bar is currently the average, and I've adjusted it to the median value. So see how some are 1s and some are 0s? Well, that's just telling us what the most common value was. A median, remember, is the middle value, and the only values in purchase bike are either 1 or 0. So now it's changed it to this weird thing where these 3 are 1s because that was the most common, and then these 2 are 0s. Yeah, that's not really what we wanted. Let's instead of using purchase bike, how about let's go pick a different y value, like age. There we go. So now we're comparing the age of each level of education, and we still have this error bar right here, which is kind of interesting. Well, let's keep this chart, and let's adjust that error bar to represent something else. Instead of error, how about standard deviation, which is the spread? So to do that, we're going to change this CI, or confidence interval, to, this is just the name they use for that bar. Let's set this to, I think SD. That'll change it to the standard deviation. Oh, I always forget my comma. All right. The reason why I want to see the standard deviation is because one of the assumptions, as you might remember from the last video, one of the assumptions of ANOVAs and t-tests is once again that the numeric label is, or that there's equal variance across all the groups. So when I make this bar with SD, I'm hoping to see, so standard deviation is just the square root of variance. I'm hoping to see that these bars are all pretty close to the same length, which they are. So I feel like that assumption is satisfied, and I'm happy with continuing on to analyze education and age. All right, next, let's learn, one more feature, one more style attribute I'm going to cover before different charts. Let's look at colors, or, no, I'm sorry, palette. There we go. And there's a full list of these that you can find in the Seaborn documentation. I know a couple of them off the top of my head, like blues, blues D, comma. There we go. Just gives us the range in a single color like that. All right, we've styled our bar plots. Let's use a slightly different type of plot next that can give us a little extra information that we don't get out of a bar plot. In particular, one that will allow us to view 3 or more features instead of just 2. The simplest and easiest way to do that, let me just copy, we're going to stick with the bar plot object and simply add another, I'll put it down here right after these. We're going to add one more attribute, and we're going to, instead of using X and Y, we're going to use something called hue, and we're going to set this equal to, how about, no, let's do purchased bike. Oh, sorry, I'm using this notation where I need df bracket purchased bike. And it breaks it apart for us like this. We can see that at almost every level, those who come into our store are more likely to purchase than not, except for, looks like partial college is slightly more unlikely. But then as we get to graduate degrees, we find this bigger difference here, where those, if they're willing to come into our store with a graduate degree, they're much more likely to purchase than others when they come in. Well, that's pretty useful. What if we take this to another level and add a 4th feature? There's some pretty cool ways to do that. So copy this, and let's come down here and let's add, let's see, we've got X, Y, hue, oh, call. And under call, let's put homeowner. And we also need to change this from a bar plot to a cat plot. Cat plot is the base object, and there are lots of varieties of the cat plot. We'll start with the default one, but first I think we're going to get an error if we run it like this. Yep. So what we need to do to fix that is the cat plot wants a slightly different format. It wants us to set the data equal to the data frame, and then rather than say x equals this whole column, just mention the name of the column, since we have the whole data right here. So we don't need to pass in the data a second time. We just need to tell it what name to use for X and Y. And hue, and call. Oh, which I already did that way. All right. So we've got a few error messages here. First one, it says facet grid object has no attribute x tick labels, get x tick labels. So facet grid is the grid underlying how the cat plot is laid out. We just simply take out this input parameter. It's kind of annoying. Each visualization has its own little unique intricacies of how we use it. Anyway, what this does for us is it creates us two different plots, one where homeowner equals yes and one where it's no. And then within each one of these bars, it then gives us the mix of purchase bike, light shaded for zeros, dark for ones. Or we could take off this palette. This palette might be less helpful now because those are too close together to see. We could let it go back to its default. There we go. Orange and blue are a lot easier to see. That's kind of neat. What helps here is you can see how spread out each one of these are. So for partial high school, this bar represents the median value, the whole height of the bar, but then right here are the individual values for age within purchase bike. So we can see there's a lot of youngers, a lot of older, and very few in the middle compared to like bachelors where we have a lot down here and then a few olders. All right, that's kind of interesting. Let's modify this a little bit more. This time, let's change the kind of plot. So cat plot is the base plot. I think I'll come down, no, I'll do it up here. And just simply use the keyword kind. Let's do a boxin plot. Oh, you know, I'm on the wrong line anyway, I meant to do that down here. Whoops. Palette blues. Boxin, sorry, I messed that up just a little bit. Get rid of palette. Back to where I was. And then let's copy this down to here. Then let's add boxin, or sorry, kind equals boxin, a comma. There we go. So this is a boxin plot, not exactly the same as a box plot because you can see the long spines are these, I guess, skinnier extensions of the inner quartiles. And it breaks up into not exactly quartiles. So it kind of gives us a more, the middle part is inner quartile range, but these are not a quarter each. And then we still have outliers out here. I'm not going to go into the details of how to interpret this plot because I want to save time and just show you some options. Let's change this to an actual box plot. So you can see we get the same thing with box plots representing quartile 1, 2, 3, and 4 with outliers. You can see boxin is a little bit more liberal about what it calls and allows an outlier to be. That's pretty useful too. We still got a couple more I want to show you. Let's do, let's change the kind to a point plot. Kind point. That's kind of interesting. Again, not going to go into the details of a point plot right now for time's sake. Let's do one more though. Let's make this one a swarm plot. Oops, wrong one. All right, there we go. It's giving us a little warning here. A swarm plot won't overlap dots like the default plot will. And so it's saying, hey, we can't fit some of the data on here because it's too wide. You got to make the visualization a bit wider. No big deal. I'm just going to leave it like that for now. One more thing I want to show you on plot options. Now this one is a rare case where it's not available in Seaborn, so I'm going to do it in Matplotlib. So I just copied and pasted some code from chapter, what was this again? 18.2. Same place we just were before, and let me tab this back here a bit. Let me show you what it does first and then explain what's going on. So this is our stacked plot. The way we do this, so this is a totally different data set. Stacked plots only make sense when you have a category that adds up to some meaningful total. Like in this case, sales by quarter and location. The category is quarter, but the different quarters have a summative property, meaning by adding them up, it makes sense to add them up. You wouldn't add up the purchase bike numeric for each level of education. Well, I take that back. I guess you could. But anyway, in this case, the way we do this, we just have some made-up data right here in a data frame with the different sales. I got to do some work to flatten these values for matplotlib. And then what I'm actually doing here is creating 4 different bar charts, or 4 different bar plots. And each one is actually the full length. So the red, that's quarter 4. Notice that quarter 4 sales are all taller or higher than the rest here above it. So by putting quarter 4 down, and I put it down last, but I'm telling it where to, basically where to appear. It's going to put the other plots on top of it. So this green one similarly goes all the way to the bottom, but you can't see that because the orange is on top of that and then the blue on top of that. So it looks like it's just plotting this little chunk, but each one of these is actually plot all the way to the bottom. I know I'm skimming over this one really quick, but there's more important stuff I want to get into and still keep this video short. So I'm going to move on to section 3 of this chapter. I'm in 18.3, and I want to talk about comparing groups. So for this example, let's go back to our bike buyers data, and in fact, let's compare education once again to purchase bike. Now, before I do this, let's simply get an overall effect size. This is what we did in the last chapter. So I'm going to paste this in from section 3 of this chapter. And let's see, we've already got our data. I don't need this again. I'll take that out. I'm going to use a slightly different version of this right here that I've got in a better format. I am going to, oh no, that's it. That's the one I want. Let's just go ahead and run this. So DF education, let's see. Oh, right here, I made this new data frame. So I did need that. Clean bike buyers once again. All right, so now I have my data, my overall F from a one-way ANOVA, and my p-value. So I can see there is an effect, a relationship between the various levels of education and purchase bike. All right, that's useful to know, but do I know, actually let me show you one other thing. Since we have an education rank along with education, that gives us the opportunity to also treat this as a number-to-number relationship, right? So we can do r comma p equals stats.pearson. We've already pulled in stats, so we can just go straight to Pearson r and pass in df, this time education rank, and df purchase bike, because we changed purchase bike to a 0 and 1. So then I'm going to copy this down to make life a bit easier. Rather than printing out F, we're going to print R. Change that to R right here. Okay, in both cases, whether we treat education as independent categories or an ordered rank, in both cases we have a very significant effect. So this says as education goes up, the likelihood of purchasing a bike goes down. Is that what we saw back up here? Actually, yes, that's exactly what we saw. So what I want to do next is let's simply pull in, let's pull this back in down here, just as a reminder of what we're working with. Although I do, no, I'll leave it like that. Okay, so we know there's an overall effect based on both this R and this overall ANOVA F. There's an overall relationship or an effect of education on purchase bike. However, do we know that the difference between partial high school and high school, for example, is that significant? Probably not, I'm guessing, but maybe is partial high school to high school significant? Let's find out. So the way we do that, as you might remember, is with a t-test. So simple t-test here. I'm going to copy and paste this in from chapter 3 for time's sake. So all we're doing here is passing in, oh, this should be a T right there. All right, let's run that. Okay, comparing partial high school to high school, these two right there. Large T, that is significant. Well, what if I want to compare partial high school to, or high school to partial college? Let's change this one. I can run it again, I can find out, oh, nope, not significant. So I could go through and do that for every one of these, but even better would be if I could go through and just write a routine to check all of them for me. All right, we'll get to that a little bit later, but before I do that, think about what that means. How many comparisons was that going to be? Well, that would compare partial high school to high school, that's 1. Partial high school to college, 2, 3, 4. And then I got to compare high school to partial college. Don't have to compare it to partial high school because I already did that. So I'm up to 5, 6, 7. Partial college to 8, 9. Bachelor's to 10. That's 10 comparisons. Well, that's not too bad, but what if I had one more value? What if there was 6 values? That means I would have 15 comparisons. If I had 7 values, 21 comparisons. Well, if you make 20 or more comparisons, even if there is no relationship between the category and the numeric label whatsoever, by sheer luck, one of those comparisons will likely be significantly, statistically significant. Because by definition, we interpret significance as 0.05 or a 1 in 20 chance. Well, we don't want to make that mistake of thinking something is significantly different when really it was just the sheer luck of doing so many pairwise comparisons for t-tests. So what do? Well, we simply make an adjustment to make it a little harder to consider something statistically significant. There's 2 ways of doing this. There's the tukey method, which is easiest to do in Python. We've already imported pandas. We're going to say from stats models. You may not have, I'm not sure if we've used this in this class or not. We'll use stats models a lot. We're going to import stats models.stats.multicomp. From that, import a multi-comparison. All right. And we're going to make an object MC equals multi-comparison, and we're going to pass in df purchase bike, and then df education. All right, and then, oops, I didn't mean to do that. And then let's print mc.tukey. This is called tukeyhsd. All right. As you can see, very easy to run this using the stats models package, and it prints out a table of every possible combination of pairwise comparisons between a categorical feature and numeric label. So it tells us we've got group 1 compared to group 2. Here's what each of them are. Here's the mean, the difference between means between those, and then here's what it calls a p-adjusted. So this is a p-value that's been adjusted to be a little more conservative and difficult to get below 0.05 in the way that it's calculated. So this is one technique, and you can see here where it says true. Now only 3 of the comparisons are statistically significant. Whereas before we would have found out that some of these other ones, like bachelor's to partial college, let's see. Let's compare partial college to bachelor's. All right, this one says it's statistically significant. But after making a conservative adjustment, we find out right here that it's actually no longer statistically significant. That's the difference between these 2 right there. Interesting. Okay. So tukeyhsd, very quick and easy way to do this. I like another method called Bonferroni. Let's do that one next. So Bonferroni takes a little more time to write it, but it is simpler to understand. So first of all, we need to write a loop that's going to go through and count and perform each of the t-tests for each of these pairwise comparisons. Now this code is probably one of the more complicated things you'll have to learn or follow along with in this class, but let's break it down together. All right, so let's start by storing each of the unique types of education. So I'm going to call this etypes equals df.education.unique. All right, that gives us a list, And then let's make a blank just so you can see. Sometimes it helps just to print it out so you can see what it actually does. There we go. There's our e-types. Let's make a list to store our t-tests in. So that's our t-test list. It's empty for now. Now let's go and loop through each of the education types. So let's say for, and let's say I, comma, E in enumerate E types. So as a reminder, if you haven't seen this before, what is going on here? Well, E is going to represent the actual education group name. The I get when I use this enumerate function. Enumerate says just keep track of the number at the same time you're looping through. So an easy way to really see what's going on here is let's print out I, comma, E. E, and maybe we better put a little something in between there like that so we can see what's going on. All right, so we've got, I guess it already built in a space. 0, 1, 2, 3, 4, enumerate 0 base so I can access the number with the variable I can access the name with the variable E. Okay, let's delete that out of there. And next, this is where it gets a little complicated, but we're going to need a nested loop. For I2, E2, and let's enumerate the same thing, enumerate a second time, E types. What does this do for us? Well, let's print them all out now. Print, actually what we'll do, I should have kept this one back up here, just so you can remember, I, comma, E. And then down here, let's print I2, E2. So here's what we've got. Bachelor's, oh, you know what I'll do is, let's put a, I was going to say we could say end equals null on that one. That only gives us one, so it's bachelor's. And then right here, I'm going to print I again. Or instead of I2, I'm going to print E again right here. And up here, instead of printing E, I'm just going to say print the iterator. So 0, I'll just take this one off entirely. So if I just print out E and E2 each time, what I'm doing here is I'm looping through, and the first one alphabetically is bachelor's in this outer loop, and then I'm looping through all of them again in here. Well, I don't want to compare bachelor's to bachelor's, but I do want to compare it to high school, partial college, graduate degree, and partial high school. Down here, I don't want to compare high school to bachelor's because I've already got that right here in the opposite direction, which is the same thing. And I don't want to compare it to itself. I just want these three. Then down here, similarly, I just want these two because the rest are taken care of. This one. And then right here, I don't need, or do I need any of these? Let me see if I can think here. Partial high school. I've already got that with graduate degree right there. I don't need it with itself. Partial college, I've already got it right there. High school, I've got it right there. Bachelor's, yeah, so I don't even need this last one right here. So how can we, what sort of if statement can we write to keep us from having to do all those repeats? Well, how about this? We're keeping track of the i's. Let's say if I2 is greater than I. Well, what does this mean exactly? Whoops, greater than I, not 1. Let me show you what's going on here. Before I do that, let me substitute in here I1, comma, E, and then let's put in just something to separate these things. I2. Whoops, I meant to do a comma there. One more time. Okay, so see how the I right here is 0, and then I2 is being iterated within each outer loop. So if I say if I2 is greater than I, then proceed with the comparison, what will that do? Well, right here it's going to skip this one because 0, and that's this 0, this is I2 right here. This 0 is not greater than that 0, but so it'll ignore it. However, this one is greater than that, so it'll do all of these. Down here, this is the first one that's greater than this one. So it will do all of these. This is the first one that's greater than that one, so it'll do just those. Down here, it'll do just this one. And at the bottom, none of these will be calculated at all. Is there a way to skip that last one? Yeah, we could say, yeah, no, not in a simple enough way. I'm just going to leave it for now. Okay, so let me take this off. Hopefully that makes sense to you, how this if statement keeps us from repeating t-tests. Now we're going to actually run the t-test. So to do that, let's trying to think of the simplest way to do this. Let's go ahead and make G1 equal to df.education equals E. Yeah, that's fine. And then we can even take that, add on to that purchased bike. So that means G1 is going to be the list of purchased bikes, zeros and ones, where education equals whatever E1 is. And the first time through, that's bachelor's. Group 2 is going to be equal to E2, purchased bike. So it's going to be the list of purchased bike numeric for this side. So group 1 is going to be the list of bike purchasers for this group. Group 2 is the bike purchasers for that group. All right, once we have that, then the t-test is pretty straightforward. TP equals t-test IND, and we'll pass in G1, G2. Okay, that looks good. Once we've calculated this, let's append it to our list. So t-test.append. How do we want to put this in? Probably we better do a list of lists. So right here we'll put in a list including, let's format it in some way, like well, group name. So we'll say E. I better F string this thing. All right, E. Let's say dash E2. And then let's give it a number there for what the t-test is. So then we can, we'll say, let's in our list here, let's put the t.round to 4 decimal places, p.round to 4 decimal places. There's a few ways you could put this string in. It's kind of up to you. I don't have to make it a list. I can make this all one value. In fact, maybe I will. I think that might make a bit more sense. Sorry that I'm changing my mind back and forth here. I'm trying to just make this example as simple as possible. Okay, T round and P round. There we go. There's our F string. So it's going to give us the group name, like bachelor's to high school, T value, P value. So we could probably put a comment in between these or something like that. That might look nice. Okay, so we've appended that to our t-test list. When that's done, let's print out what we're looking for here. So at the end of that, let's run, and let's say print. Let's do an F string, and let's say something to the effect of t-tests below. You know, let's save this for now. I'm going to come back. I'm going to hold on to that. So I want you to see what's going on first. Let's simply print t-tests so we can see if this works. Okay, what do I miss here? F string. Oh, I missed a curly brace at the end of this one. Is that it? Did I miss one more? Oh, I forgot to add or take off this bit of the list opening right there. Oof, I keep missing things. Oh, I've got one extra parenthesis right there. Okay, name t-test. Oh, because I got to refer to it by stats.t-test. There we go. So in fact, let's print these out. And maybe I can just print them out up here as I go along. Print this F string to see if that looks right. There we go. So here's what I'm getting out of this. Each one of my comparisons without repeats with my t-value and my f. My t-value and my p. Well, we don't want to always have to print out this gigantic list. What if we just print those that are significant each time? That's what I was getting at with this right here. So now that we see what this is going to look like, I'm going to remove that and say, let's print out t-tests, significant t-tests. T-tests. And then let's below, and let's give it a threshold. So now is a point where you're going to learn how the Bonferroni works. So for Bonferroni, now that we've calculated every t-test, what we do is we say 0.05 is no longer the criteria or the cutoff. The cutoff is going to be equal to the total number, 0.05 divided by the total number of tests. And that's going to be our new threshold for what's significant. So right here, let's just make a new variable and call it threshold equals t-test, length of t-test, len t-test, divided by 0.05. So that's the way the Bonferroni works is rather than change the p-value, we're simply changing the threshold or the cutoff for what constitutes a significant p-value. And we're going to print that out right here. Let's see what that turns out to be in this case. Whoops, I've got it reversed. Sorry. It's 0.05 divided by the length. There we go. So because there were 10 comparisons, the new cutoff for what constitutes a significant t-test is 0.005. Okay, so now all I want to do is go through and say for, I don't know, L for line, or here we go, T in t-tests. If, oh, I see, that's why I had it separated out right here into a list. Yeah, I'm sorry. I'm going to have to go back to that again. Let's make this a list here. I apologize for making you go back and forth, but I thought I'm going to leave this in the recording because sometimes it's easy for you to see my own thought process and how I fix things for yourself. So I'm going to remove that, make this part of the string right here, comma. So now I am inserting 3 values in a list right there. And so I want you to be able to see what is going on and why I'm doing it this way. So I'm just going to print this out for you real quick. Let's print that out, and then let me just comment this out temporarily. So see, what I'm doing is now, as I'm in t-tests, I'm appending a list of, or each item itself is a list of 3 values. That's all. So what that lets me do is access this by index. Oh, I don't need these now that I'm no longer in an F string. There we go. A list of 3 items, the comparison name, the t-test result, the p-value. All right, we get rid of that. Whoops, not that. Okay, down here, let's uncomment that. We got our threshold for T and T tests. If T1, which is going to access this second item in the list, if T1, actually that's not what I want T2, I want the last item in the list. If T2 is less than or equal to the threshold, then we're going to print it out. In that case, I'll go ahead and print all of, I'll just go ahead and print all of T. That's fine. Let's see how that looks and see if we like it. All right, significant t-tests below 0.05. Here's the only 3. Are these different than what we got up here with the tukeyhsd method? Let's see. Bachelor's to partial high school to partial college, right there, and then graduate degree to partial high school. Sure enough, we get the exact same results either way. So either one is fine. What I like about this technique is that it, well, I guess either one would be okay, because you could drill into tukeyhsd and just pull out those that have a reject set to true, or a p-value right here, p-adjusted below 0.05, so either one's totally fine. All right, we know how to analyze the stats. We know how to visualize the relationships. Let's put it all together now into one final example where we embed the text into a chart. So to do that, I'm going to go ahead and copy in, well, I'll start with this, and let's just go through and for each, let's make the chart, and then let's embed a list of these things right here, and also the overall F score. All right, so to do that, I'm just going to simply build out, I'm going to build out a string. I'm going to start this right about here and say text, we've done this in prior chapters, equals F, let's say, let's put ANOVA in there, and maybe a new line, and maybe we'll kind of try and center this a little bit by adding some spaces. And then I'll say, we better call this actually text str, just so it doesn't get confused later, plus equals, so append onto that, F, and let's insert F, and then let's say, let's stringify here, where's our ANOVA that we ran earlier? Right here. So we still have F and P in memory. So right here I'm just going to simply say string, well, I don't have to stringify it there, I can just put in F, oh, mark, F, and let's line break to the end of that, at the end of that, and then I'm going to start copying this. P. Now let's see, we overwrote P previously, so I better come up here and change it, or just bring all this back down again, either one. I'll just rename this to something else. FP. FP, so that still works. Then I can use that one down here because it's different. FP. All right, now for the rest of this, let's make another header here, and I'm going to call this Significant Comparisons Bonferroni. No, it's 2 R's. Using a Bonferroni adjustment. And then let's add a line break at the end of that. And now here is where I want to go ahead and start. Instead of printing it out, I'm going to simply add it to the text string right here. So text str plus equals, and we'll add in T. All right, yeah, that'll work. Well, now I'm going to be difficult. I don't want it to show the list, so I'm going to say T0, and that, and then I'll add in some spaces, and then add them each one item at a time right there. That'll get rid of the brackets. All right, lastly, we just need to add it to a diagram or a figure. I'm just going to grab this one right here. We'll bring it down, use it right here, and we just need to add the text to it. So we can do that by saying plt.text, and we're going to position it, I don't know, I'm just going to take a guess at first, 1, 0, and then we're going to pass in the text str, text string, there we go, and we're going to set a font size, something like 12, I'm just guessing, we might need to adjust that. And then we do need to transform equal to plt dot, this is just the layout, GCF dot trans, I think it's transfigure. We'll see if that works here. And then that's it. Let's see if we got it. FP is not defined. That's right. I got to run everything up to here. I didn't run that cell previously, so let's run all. Give this a moment. We're so close. So close. Let's see where we're at. Right there. Right there. Here we go. Significant tests. It printed this out right here. Oh, you know why? Because I didn't include this guy right there. Oh, where is it still? Oh, it's printing this out right here. I don't want that one. Okay. Oh, the only thing I'm missing is at the end of this, I need a line break. /n. There we go. We've got our diagram, and then we've added here the ANOVA results. Yeah, we should probably round those. That might look a little bit nicer. There we go. We got our F, our P, our list of significant comparisons. Maybe I'll space that in a little bit so it looks a little more like a title, I guess. There we go. Yeah, you can play with it and make it look the way you want. But that's all the relevant statistics, the relevant chart. We are done analyzing categorical to numeric relationships. No, this was a long one, but I hope it was useful for you. Next video, we'll get to work on categorical to categorical relationships.